Let's now take a look at a simple example of a classification task. So the data set that we're going to use is represented with this plot. So the idea is that we have two features. Let's call them x1 and x2, represented by our two axes. And every observation has a value for each of these features, x1 and x2, but then it also has a categorical label of either orange or blue, as indicated by the color of the point. So looking at the original data, you can definitely see that there is a relationship between a point's position within this x1, x2 plane and its color. The orange points seem to be mostly clustered in this lower left-hand corner, whereas the blue points are clustered sort of outside of that corner. However, the relationship is not perfect. There's definitely some overlap, and you see some points here where some regions where there is a fairly even mix of orange and blue points. So what we would like to do is create a model that takes as its input x1 and x2 and predicts a label, orange or blue. For example, if I plug in x equals 4, x1 equals 4, and x2 equals 3, I get this point, which I would hope that my model would probably classify as orange. If I plug in something like 8, 6, then I get this point, and I would probably want my model to classify that as blue. However, if I plug in a point like 6, 4, I get a point right here, and it's maybe a little bit more ambiguous as to whether or not my model should classify that as orange or blue. As with regression, there are many different types of algorithms that we can apply to a classification task. Each of these algorithms will produce a model that generates predictions in a slightly different way. We will discuss the different types of algorithms in more detail later, but here, just as an example, I've shown you 5 plots that show you the classifications generated by 5 different types of models. You might want to take a minute and pause the video and take a look at each of these models on your own and see if you can get an idea of which one you think personally is the best. So here are some things to consider. So we start off by using a logistic regression algorithm. Again, we'll discuss the details of that algorithm later, but the idea behind a logistic regression algorithm is it always creates a linear boundary between your two classes. So this line, so basically our boundary is this line here. On one side, we predict orange, and on the other side, we predict blue. That does a reasonable job of separating the orange and the blue points, but looking at the data set, I would probably not have guessed a linear boundary would have been appropriate. I would probably have, if you just asked me to draw a boundary by hand, I would probably have drawn something like this. So there's another more advanced algorithm called a support vector machine that, when applied to this data, actually produces a decision boundary that looks a little like that. So that's much more in line with what I would have expected just by looking at the data. There are other modifications. The support vector machine algorithm has a lot of different options that you can set. If I change those options a little bit, instead of getting a decision boundary that looks like this, I get something that looks like this. Again, this does a pretty reasonable job of separating the orange observations from the blue observations. However, I would say that this model is probably overfitting a little bit. Notice that we get this sort of complicated, semi-complicated boundary in order to accommodate or predict these few points correctly. Now, that in and of itself is not unreasonable. It may be that you would want to classify a point in this region as orange. However, notice that we also have this little island of orange over here that is solely based on this one little point. If I looked at my original data and I picked a point right here, I would probably be inclined to want to classify that as blue. But here we're classifying it as orange because of that point. So this is probably an example of some slight overfitting. If we apply a nearest neighbors algorithm, a one nearest neighbors algorithm to this data set, we get a boundary, a really complicated boundary that looks something like this. Now, this does a really good job of correctly predicting the classes for the data that this was trained on. In fact, it gets every observation correct. However, the decision boundary or the decision region is this really complicated shape that probably is not going to generalize well. Notice that we have all sorts of little islands of orange within the blue regions and also some little islands of blue within areas that we would maybe expect to be orange. This is probably an example of severe overfitting. This model does very well on the training data, but will probably not generalize well. As another example of overfitting, we have a model here produced by what's called a decision tree algorithm. Again, we have really good predictions on the training set, but our boundaries are really complicated and are probably not going to generalize well. As a really good example of this, notice that you have this thin line here of orange. If you pick a point anywhere in that line, this model will predict that it is orange. It's generating that prediction solely because of this one point, which is probably not reasonable. If I pick a point over here, I am almost certainly going to want to classify it as blue and not orange. So again, this is an example of overfitting. We've come up with very complicated rules that do well on the training set, but don't generalize well. As some additional information, later on, when we're deciding on a model, like if we're considering multiple different kinds of models and we want to decide which one to use, we need to have a way of scoring those models. One metric used to score models, classification models, is their accuracy. The accuracy is just the proportion of the number of observations for which the model generates correct predictions. And you can calculate accuracy in a couple of different ways, but for now, just talking about calculating accuracy on the training set, we get the following results. Our logistic regression model gets roughly an 85% accuracy, 84.7%. The support vector machine model with the polynomial kernel, this model 2, gets an 89% accuracy. Model 3 gets a 93% accuracy, and model 4 and 5 both get 100% accuracy. But again, you don't want to rely on accuracy by itself, because as we saw, models 4 and 5, even though they do get 100% accuracy, that's because they are overfitting to the training data.